Imagine a countdown clock ticking down to the exact day a major modern city literally just runs out of water. No water in the taps, nothing in the pipes. In 2018, this terrifying reality almost hit Cape Town, South Africa. They called it Day Zero. It was the projected date when the dams would hit critically low levels, forcing millions of residents to queue up in the streets just to get a daily water ration. People had to radically change their habits overnight, slashing their usage just to keep the city from completely collapsing. It was a massive global wake-up call. But here's the scary part. Cape Town was really just the canary in the coal mine. Between rapid population growth and climate change messing with precipitation patterns, major cities like Jakarta, London, and Tokyo could all be facing their very own Day Zero in the coming decades. This is a very real, global threat, and it's exactly what we're exploring in today's Explainer.
Welcome to The Explainer. I am so excited to take you on this journey today. We're going to dive deep into how cutting-edge innovations are stepping up to solve the world's most pressing resource crises. And look, we aren't just talking about slapping a Band-Aid on things here. We're looking at how brilliant minds across the globe are building a sustainable society from the ground up. They're engineering entirely new ways to harvest, manage, and recycle the absolute essentials we need to survive.
Okay, let's dive right into this. Here is our roadmap for today. First, we'll look at innovating our water supply. Second, transforming waste into power. Third, decentralized clean energy systems. And fourth, smart factories and grids.
All right, Section 1, innovating our water supply.
Let's start with our most critical fundamental need, water. As we saw with that whole Day Zero crisis, our traditional water sources are under an unprecedented amount of stress. Rivers are drying up, aquifers are shrinking, the gap between supply and demand is closing way too fast. Now, our planet is covered in over 1 billion trillion liters of water, right? But here's the kicker. 97% of it is salty ocean water. Another 2% is locked away, frozen in ice caps. So that leaves us with less than 1% of the Earth's water that is actually drinkable. Less than 1%. Naturally, desalination, taking the salt out of seawater, seems like the silver bullet. But historically, boiling millions of liters of water or pushing it through these massive membranes takes a huge amount of energy. It's historically been incredibly expensive and super reliant on burning fossil fuels.
But, the paradigm is definitely shifting. Take a look at this incredible example. There's a startup called Boreal Light running a desalination plant in Kenya, and it is entirely powered by green energy. By hooking up solar panels and wind power, they've completely eliminated the cost of grid electricity. They can actually produce 1,000 liters of clean, desalinated water for just 50 cents. That is a total game changer for off-grid communities. Now, it's not a perfect magic formula just yet. The industry still has to figure out the brine issue. When you extract fresh water, you're left with this super salty brine, and a lot of times it just gets pumped right back into the ocean where it depletes oxygen and suffocates marine life. Fact is, we're currently producing more toxic brine globally than we are fresh water. So figuring out how to manage that byproduct is absolutely crucial.
But hey, the ocean isn't our only untapped water source. We can literally pull water right out of the sky using something called atmospheric water harvesting, or AWH. There are two main ways to do this. Active systems use external energy, like a refrigeration cycle, to pull massive volumes of moisture from the air. But then you have passive systems, which use zero electricity, none. They just rely on natural temperature shifts. In places like remote Chile and Morocco, they set up these massive fog nets to catch moisture rolling in. And it gets crazier. Researchers at MIT have developed these passive hydrogels, and scientists are now using metal organic frameworks, or MOFs. These are these highly tunable materials that act like microscopic sponges, pulling drinkable water from the air, even in totally arid, low-humidity environments, without a single plug in sight.
Moving right along, Section 2, transforming waste into power. So we're finding brilliant new ways to get water, but what about the stuff we throw away? For centuries, humanity has basically looked at waste as trash, stuff to be buried in a hole and forgotten about. But in this resource revolution, waste is just a fuel we haven't utilized yet. Get this, every single year, human beings produce over 2 billion tons of waste. 2 billion. To put that into perspective, that is enough to fill a line of garbage trucks stretching from San Francisco all the way to New York City every single day. And when all that organic material just sits there rotting in landfills, it turns out methane. And methane is a brutally potent greenhouse gas. We're talking about 86 times more potent than CO2 over a 20-year period.
We clearly have to do something with all that trash. Now, the old way of getting energy from garbage is incineration. But environmentalists absolutely hate incineration, and honestly, for good reason. Burning trash creates toxic ash and these hazardous chemicals called dioxins. But then there's gasification. This is the new way, and it is gaining some serious traction, even catching the eye of major investors like Bill Gates' Breakthrough Energy Ventures. Gasification doesn't actually burn the trash at all. It uses a process called molecular conversion without combustion to produce a super clean synthesis gas, or syngas.
Let's break down how a company called Sierra Energy pulls off this molecular magic. Step 1. They drop solid waste into the top of a high-temperature blast furnace, which is actually tech borrowed from the steel industry. Step 2. They blast oxygen and steam into the bottom. The intense heat and chemical reactions literally tear the waste apart at the molecular level. So step 3, out of the top comes this high-value syngas, which can be easily turned into diesel fuel, hydrogen, or electricity. And what's left at the bottom? Just a harmless glass-like stone that can be used to pave roads. Because this prevents all that nasty landfill methane from ever hitting the atmosphere, the whole shebang can actually be carbon negative.
All right, Section 3, Decentralized Clean Energy Systems.
Now that we're turning our waste into fuel, we really need to talk about how we power the grid itself. The whole future of power is moving away from those massive, centralized fossil fuel plants we're used to. Instead, we're shifting toward local, decentralized, sustainable generation. Hydropower is great, sure, but massive dams totally wreck local ecosystems. Enter a company called Turbulent. They make these low RPM vortex micro-hydro turbines. As they point out, you literally only need a 1-meter drop in a river or canal to generate power. In fact, at the Green School in Bali, they installed one of these to provide stable, round-the-clock power for 600 students. And the absolute best part? Because the blades are curved and spin so slowly, fish and other aquatic life can just pass right through the turbine completely unharmed. It's affordable, it's local, and it's truly green energy. Now, on the totally opposite end of the energy spectrum is the highly debated dual fluid reactor, or DFR. We're talking advanced nuclear here. The developers are making some massive claims. They state this new reactor can actually burn existing radioactive waste, run at insanely efficient temperatures up to 1,000 degrees Celsius, and produce zero CO2. Their ultimate goal? Take nuclear waste that would normally be dangerously radioactive for 700 million years and shrink its lifespan down to just 300 years. On the flip side, though, there is deep scientific skepticism. This liquid salt technology is largely unproven in any real-world commercial scenario. Plus, there are severe, completely understandable public concerns regarding safety, especially when you look back at disasters like Chernobyl and Fukushima.
But mechanically speaking, how does a dual fluid reactor even claim to pull this off? Well, traditional reactors use solid fuel rods. The DFR uses two separate liquids instead. First, a liquid fuel made of uranium or plutonium salts circulates inside closed pipes. Second, you have liquid lead acting as the coolant. The lead flows over those pipes, absorbing the massive heat, again up to 1,000 degrees, while also effectively shielding the radiation. That heat is then transferred to water, which creates steam to spin the turbines. So as you can see, it's a fundamentally different architecture from the nuclear plants operating today.
Right now, the DFR is heavily theoretical, but the developers do have a strict roadmap for commercialization. They're aiming to have component tests running by 2026, a working prototype by 2029, and full serial deployment by 2034. We're talking about an estimated €8.5 billion endeavor here, and it relies heavily on securing immense investment and proving, without a shadow of a doubt, that it can actually operate safely.
And finally, Section 4, Smart Factories and Grids.
So, whether our energy is coming from solar power desalination, trash gasification, vortex turbines, or advanced nuclear reactors, it all has to be managed. And that brings us to the brain of the future city, the Industrial Internet of Things, or IIoT, and the rise of smart factories and grids. See, for a long time, manufacturing relied on this really inefficient batch and queue system. Factories basically just kept machines running constantly to lower their per-unit costs, regardless of what the actual demand was. This caused massive bottlenecks, and if a machine was making a defective part, you wouldn't even notice until the next stage, wasting tons of resources. The IIoT changes all of that through smart manufacturing. By using predictive AI and thousands of sensors, edge computing networks process data right there on the factory floor in real time. They can actually detect machine issues before they cause downtime. Plus, they empower augmented operators by beaming real-time data straight to their mobile devices or AR glasses. The factory becomes flexible and user-centric, instead of just blindly machine-centric.
But it's not just giant factories, it's our everyday infrastructure. Companies like Eaton and Siemens are pushing to turn our very buildings into local energy hubs. Think about it for a second. As we all transition to electric vehicles over the next decade, the demand on the power grid is going to be absolutely staggering.
Instead of doing wildly expensive grid upgrades everywhere, our buildings will use energy intelligence. A massive logistics center, or even just your own home, will use local battery storage and solar power to balance peak loads. Your house will know to charge your EV when power is cheap and abundant, and it'll hold off when the grid is heavily strained. Everything becomes an active, participating node in this interconnected, highly secure digital web.
And man, do we desperately need this intelligence. According to the International Renewable Energy Agency, cities account for a staggering 65% of global energy demand and 70% of energy-related emissions. Making our urban infrastructure smart isn't just some fun tech upgrade. It is quite literally our single biggest lever for combating climate change.
We've covered some incredible ground today. We've seen how desalination and pulling moisture out of thin air can secure our water future. We've seen how blast furnaces can magically turn our rotting trash into clean fuel. We've looked at micro-river turbines, theoretical reactors, and the brilliant, intelligent grids required to balance it all out. We are actively moving from this old age of extracting and burning to a new age of harvesting and recycling in a closed, intelligent loop. But here's the truth. Technology alone isn't enough. It requires a fundamental shift in how we live day to day. So I want to leave you with this thought. If our entire future relies on this highly connected, sustainable loop, what old, inefficient habits are you willing to leave behind to help power this new grid? Thank you so much for joining me on this Explainer today. Keep learning, keep questioning, and I'll see you next time.